So these type of integrals come up a lot in physics, so let's take a look how to tackle them. So first of all, we see that this part is dqi and this part is dpi. And everything in the integrand is only with respect to pi, so the dqi's essentially break apart on their own, and they can come out on their own with like that. And we'll pull out any constants over there, and left with this. So how do we interpret this? Technically, the 1 over n can also go outside of the integral, and the integral is only with respect to dq over here. So if I have normally just dx, or dx with respect to a certain interval length, somewhere from a to b, let's say with this length, then the result is just L. Or if I have 3 dimension, and if I want to integrate through some volume, d3x, then the result is just a volume. So here I have, d3q, so I have n amount of these, so each d3q, so each of these gives me a volume, and if I have n number of them, it'll give me n number of volumes. So this part basically just gives me v to the power of n. So now we'll just deal with this part. So this is a standard integral called Gaussian integrals, so let's look at that specifically. So let's specifically look at Gaussian integrals. And the most basic, before we tackle a multidimensional one, let's basically do the first one, do a simple one-dimensional one, and we start off with e to the minus x squared. So this one, the answer is minus pi, square root of pi. So this is a standard result that one would want to memorize it for future convenience. So, and then we can start to build up more complicated ones. For example, if I have a coefficient in front, and this would be easily do by a simple u substitution, and the answer will be pi over a. So these two are actually pretty standard results that would be very beneficial to actually have them memorized. But I would start with definitely the first one, having this come into memory, and then if you have spare memory in your head, you can remember this secondly. So why is this? So let's make sure we understand how we do that. There's many ways to evaluate this, but the simplest and most elegant one is to consider doing a double integral. So let's call this I, and let's evaluate I squared. So that means we can write this as this times itself. However, just to make sure we don't, the dummy variables don't cross each other, we'll use a different dummy variables for the second one, because x and y are just dummy variables. I'm free to use whatever I like. So now that I have 2 of them, I can actually rewrite them like this. And now I can do a simple change of variable into polar coordinates. Remember the Jacobian over there. And nicely enough, there is x squared plus y squared is actually just r squared. So in the polar coordinates, this actually separates out to d theta and dr, whereas the first one is just 2 pi, and the second one is a simple u substitution. So that gives me 2 pi 1/2 minus e to the minus r squared. Now notice the limits on theta is 2 pi, so theta goes from 0 to 2 pi, and r goes from 0 to infinity, because we're integrating through all space. In fact, I probably should have commented, this integral is only well defined, it only has a closed form if the integral is through the whole x-axis, through all space. So there's always minus infinities and infinities in all of these little integrals over here. So back to here, what we have is just 2 pi divided by 2, so I have pi, and in here I have 0 minus -1, so it's just pi. So we have I squared equals to pi, and that gives us I equals to square root of pi. So I've proved equation star, the first one over here, and to get the second one, all you have to do is a substitution. So for equation double star, what we can do is consider multiplying, 1 over root a and root a inside here. So since root a is just, since this is just a dummy variable, we can completely replace that with a different variable, for example, u, like that. So, and now we have exactly a Gaussian integral. So we can use the result from star over here, and we know that this is, we must also double check the limits, because x goes from minus infinity to infinity. When you go to u, it's still minus infinity to infinity, because if x is plus or minus infinity, u is the same as plus or minus infinity. So the limits don't change. So this is exactly a Gaussian integral, which is root pi. So now we have the results. So we have these two most important results. So let's go back to the original one over here. So if we remember the original one over here, we should be able to break it out. Let's use yellow. From 1 to n, d3 pi, and e to the minus beta to m. So first of all, there's a sum over here, so we should be able to break this out first. So when you get to this step, just be careful of the notation over here. This product actually just means the product on the measures. This is its own thing. So really, the first part, what we could do is write d3 p1 dot 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 d3 pn. So all the way from 1 to n. And then the second part here, we can write this as minus p1 squared 2m times e to the minus p2 squared 2m up to pn squared 2m. So notice that the p1 integral only acts on this factor, and the pn integral only acts on this factor, the p2 integral only acts on this factor. So we can actually write the first part just like this. So p1, and we can write the p2. So this one is exactly the same, but for p2, and then all the way multiply to the pn integral, like that. However, you see that the p1s, p2s, and pn's are all just dummy variables. So if they're dummy variables, these basically just collapses because they're all the same thing. Each of these brackets are all the same. Oops, I meant p1 over here. So we can just write it like this to the power of n, because every single brackets over here, we have n of these things, and they're all the same. And this is precisely one of these integrals over here. In fact, it's the second one with a coefficient a, so we can directly quote that result over here. So the result of just the yellow part over here would be square root of pi, and this time our a is everything over here. So we have beta over 2m, and we can simplify that later. But be careful, there's actually 3 integrals over here. When we say p1 squared over here, we actually mean p1x. For example, so this actually means p1x squared plus p1y squared plus p1z squared, like that. So this whole factor should be broken up into the p1x part and over 2m plus p2 squared over 2m, etc. Sorry, p1y squared over 2m, and because it's an addition on the index, that means it's a multiplication of factors. So technically, this actually has 3 parts as well. So we need to put a cube here before we should do the n. Another way to look at that is I could have written p1x and e to the minus beta over 2m p1x squared, and consider that there's 3 copies of these, because this is actually p1x squared plus p1y squared plus p1z squared. So there's 3 copies of these, and there's so there's 3 n copies of the standard Gaussian integral, where this is the a on this side. Okay. And that, of course, gives the same result, square root over a to the power of 3n, where a is this factor over there. Okay, so now we're ready to tie everything back together. What do we have in here? We have 1 over h cubed and v to the power of n over n factorial. Okay. So combining with the yellow part over here, if we simplify this a little bit and tidy them up, we have 1 over h cubed vn n factorial, and we have, let's write this as 3n over 2 instead of the square root. On top we have 2m pi, on the bottom we have beta. And that is the full result over here. If you have any questions or comments, or if you spot that I made any mistakes, feel free to let me know in the comments below. Alright, hope this helps.